Hello everybody, good afternoon. So first I want to thank the organizers for inviting me to give this talk today. Always very happy to be here. So the title of the talk, this is not the one, the right button. Okay. The title of the talk is Phase Transition and Ergodicity Breaking in Movement of Avians. This work has started by a collaboration with the group of Ran Natan from the Hebrew University. He's a movement ecologist and he has a very rich and high-resolution movement data of various avians. And we collaborate, and our group does the theoretical analysis, and I'm very happy with this collaboration, and I think we have very nice results that I will show you. Okay, so I want to talk about two works relatively recent about phase transition in a simple animal movement model with memory. This work is initiated by looking at movement patterns of Egyptian fruit bats in the northern part of Israel. And the second part will be about ergodicity breaking in area-restricted search of avian predators. Here we were looking at common kestrels, black-winged kites, and barn owls, and we wanted to understand the difference between commuting and searches of these species. Okay, so here I'm showing you some typical trajectories that the group of Ran measures. I will discuss the GPS, the innovative GPS system that they use. It can produce very high resolution data, as I said. So on the left, you see a trajectory of a black-winged kite. You see the long stretches are commuting, and these circles, within these circles, there are the search patterns. And on the right, you see a trajectory of an Egyptian fruit bat going from their cave to some fruit trees and back. And let's first focus on the dynamics of the fruit bats. And we wanted to understand how the fruit bats explore new sites, so in what way they visit new trees, and how they revisit already visited trees, so how their memory works, more or less. So basically, any animal movement model should have these two basic ingredients: exploration of new sites and memory in the form of return to already visited sites. And I will show you how we incorporated memory in this model in a very simple manner. But of course, one can do it in a more elaborate or more complicated way. We have tried, but it turns out that the simple model captures the dynamics quite well. The problem with models with memory are that they are non-Markovian and problematic to solve, but this simple model turns out that can be solved exactly. So the model that we took is a generalization of a well-known model used by Song et al. From the group of Barabashi to model human movement, so human mobility. So this model has been used by others as well to model monkeys, monkey movement, elephants, and other animals. So the model consists of basically two ingredients. One is a probability. With probability p nu, the animal jumps to a new site, okay, so explores a new tree in this case. And with probability 1 minus p nu, the bat returns to an already visited tree, okay? So we assume that the probability of visiting a new site decays with the number of sites. So the more sites there are, the smaller the probability to visit a new site. It is a little bit similar to what Satya showed us yesterday with the random walk model. So, but this here in this case, it is a unidirectional model, as I will show you. And so this probability decays as n grows, and beta is some non-negative exponent. And the probability to revisit an already visited tree is proportional to the number of previous visits to the power of alpha, some alpha. Alpha is the preferential reattachment exponent, and the stronger alpha is, the larger alpha is, the stronger the tendency to revisit an already visited tree. Beta is called the exploration exponent, and it's basically the opposite of the tendency to explore. So should have written opposite here. So the larger beta is, the less the tendency to explore, right? When beta equals 0, then it explores basically at a constant rate. The rate does not depend on n. So as beta increases, the tendency decreases. Okay. So let me just give you some motivation of why we chose this preferential reattachment mechanism for the memory. So first of all, we were looking, First of all, we were looking at the probability distribution of the number of visits as a function of the number of visits. So we were looking at trees, and so how many trees were visited once, twice, and up to the maximum number of visits. So we saw that there were many trees that were visited very few times, and there were also some trees that were visited many times. Importantly, the tail here is a power law tail. And this immediately reminded us the well-known work of Barabashi and Albert from '99, which is cited, I don't know, over 50,000 times, about the formation of scale-free networks. So here, if you have a network and a new node wants to join the network, basically they assume that the node connects to an already existing node with probability proportional to the degree of that node. And if you do that, if you do the dynamics in this way, you get a power law distribution for the degree distribution, a power law function for the degree distribution of the nodes in the network. And in analogy to this, when one can map basically between the degree of the node and the number of visits of the tree, we concluded that this could be an adequate model here as well, which gives rise to a power law visitation frequency basically. Okay, so this is why we chose this preferential reattachment model, and importantly, in the case of Barabashi, they took alpha, the preferential exponent, to be 1, and this gives rise to a power of -3, and we loosen this constraint and allow alpha to be any number, so you can get basically any exponent here. Okay, so first of all, I want to talk about the distribution of visits to new sites. So basically, we have a process where the number of sites grows by 1, the simplest process that you can think of, but the rate here is proportional to n to the minus beta. Beta is a non-negative number. We assume it's positive actually, because when beta is 0, then it's just a Poisson process. Q is a constant. So this is the master equation, continuous time master equation. And in order to get some insight, we can look at the mean number of sites, the dynamics of the mean. So here, this is the differential equation that the mean satisfies. And the solution here is just, the asymptotic solution is just t to the power of 1 over 1 plus beta. So it grows sublinearly in time. The mean number of sites of new trees grows sublinearly in time. So apparently this master equation can be solved using the Laplace transform. One can use various techniques here, actually the generating function as well, for particular values of beta. But it turns out that it is quite complicated and intricate, so it's not trivial to solve this equation, even though it looks very simple. So the solution via Laplace transform is this solution. It's quite cumbersome, but it's exact. The problem with this solution is that it's an alternating sign summation. So the terms here have changed the sign as k increases, and they become larger and larger. So this entire sum converges due to a delicate balance between the terms. But you need a higher and higher accuracy, working precision basically of the computer to have this result for this result to be accurate. And there is a limit for the working precision, of course, unless you write a designated software. So this solution turns out to be not very useful. To circumvent this problem, we use instead so-called time-dependent WKB solution to solve this master equation. Basically, I'm not going to go into the details, the mathematical details, But basically what we do is use this ansatz, n in brackets is the mean number of sites. It is assumed to be a large number, so the number of sites is assumed to be large. S of x is called the action function. It's an order 1 function. We plug this into the master equation and get a set of Hamilton's equations, which can be solved perturbatively in the where the large or small parameter is 1 over n brackets. And making a long story short, we obtain this function for the action function. This is just a set of series of elementary functions. Everything here, f of x is given by this expression, and b is just a beta function. So you can calculate the entire probability distribution function of the probability to have n sites at time t. And you can compare this with numerical simulations of the process. So here you see the black dashed line is the exact solution, the red dashed dotted line is the WKB, and the circles are the numerical simulations, and they agree very well. This is for beta equals 1. For beta equals 1/2, we took other parameters, and we see that the exact solution, we could no longer plot it. We could no longer calculate it, so only the WKB approximation holds here, and it agrees very well with the numerical simulation. Other quantities which are of course of interest, not just the entire distribution, but the first two moments. When you have empirical data of 50, 60 fruit bats, you can't really talk about the tails of the distribution. It's meaningless. So we wanted to see how the first and second moment of the theory compare to the empirical data, which I will show you in the next slides. So the first moment we already saw, the mean number of trees grows as 1 over t to the power of 1 over 1 plus beta, t to the power of 1 over 1 plus beta. And the second moment can be computed by solving this Fokker-Planck equation. It's again similar to what Satya showed. Here you can also define some diffusion constant and some drift. Sorry, and you get a variance which is proportional to the mean divided by 2 beta plus 1. So it's a sub-Poissonian process. Okay, so let's now talk about the statistics of number of visits to a site. After establishing the distribution of new sites in this problem, let's talk about the statistics of the number of visits to an already visited site. So, as I said before, the probability to revisit a tree is proportional to the previous visits. So, the number of visits grows by 1 with probability which is proportional to pi I. This is pi I. Sorry. So, pi I is given by this expression. So, we are interested in the asymptotic, the t goes to infinity dependence of these number of visits on time, basically. We want to know how many times a tree is visited and what's the ratio and whether all trees are visited or only a few trees are visited, and this is what we wanted to investigate. It turns out that you can write down a master equation for the joint probability to find M1 visits for tree 1, M2 visits for tree 2, etc., etc. But it's very difficult to solve this for the general case of alpha different than 1. You can solve it for alpha equals 1. So what we did is look at the rate equation for the mean number of visits, and we ordered the trees by their rank. So the first tree will be the most visited, the second tree will be the second most visited, etc., etc. So this is the equation, the governing equation. It turns out that it has very interesting behavior as a function of alpha, the solution, the asymptotic solution. For alpha equals 1, it turns out that all trees get asymptotically the same visitation frequency, at least in the leading order. The amplitude is different. The amplitude is proportional to the time, basically 1 over the time this tree was first visited. So, of course, the tree that was last visited has a much smaller amplitude. But the time dependence is the same for all trees. For a weak preferential reattachment, you also get an identical asymptotical dependence of mi on t to the power of beta over 1 plus beta. You can get that by perturbation theory in solving this perturbatively. So a similar visitation rate for all sites. But for alpha greater than 1, some sharp transition occurs. And it turns out that only the most visited site receives all visits, and the other trees get nothing, basically. So you see that mi, when I equals 1, is proportional to t, scales as t, and all other trees are constant. So as time grows, as t grows, basically the frequency, the fraction of visits of the first visited tree goes to 1, and the fractions of all other trees go to 0. This can be illustrated by looking at these plots and defining the fraction of visits to a site with rank k by mk divided by the sum of all mk's. Here you see several times and the fraction of visits to the first most visited tree as a function of alpha. You see that as time proceeds, you see a very sharp first order phase transition here from when alpha is small, then this fraction is on the order of 1 over n. So all trees get the same visitation frequency, but as alpha approaches 1, this transitions to 1. So the first tree, the most visited tree, gets everything. And you can similarly see here that the fraction of visits to the first tree grows, while all others at some point start to fall down. So from this, we see that, of course, something abrupt, something extreme happens at alpha equals 1. But we can conjecture, before even looking at data, that this is a good operating point to be around alpha equals 1. Because if you are at alpha very small, then the bats visit all trees with equal probability without even caring what fruit content, what fruits are there on the trees. And this is probably not very good with respect to energy expenditure. On the other hand, if alpha is greater than 1, then the bats visit only one tree. And this is, of course, not good for risk management. If this tree is depleted, then they need to find another tree, and this may be complicated. So the best way would be to be on the verge of alpha equals 1. This is now I'm showing you some data, some empirical data of about 50 to 60 fruit bats, depending on the season. We measured these for around 1 month in each season. And measured the number of sites, the standard deviation across the different trajectories, and the number of visits to the most visited tree, and second most visited, etc., etc. Here you see them all. First of all, by looking at the mean, you can fit the value of beta, the exponent beta, which is the exploration exponent. And you see immediately that in the summer, the value of beta is higher than in the winter, which means that in the summer, the bats explore less. But this is quite understandable because in the summer, the fruits have higher sugar content, so the bats need to look less for new trees, and each fruit is sufficient for a longer time, and so basically exploration diminishes during summer. So you see that once we fitted the mean, the standard deviation excellently agrees with the experimental data, indicating that the model is adequate, at least in this sense. We also compared the mean number of visits and the standard deviation. You can also compare that, and you can also do the theory for that. I haven't shown you. And we see that, interestingly, indeed, both in the summer and in the winter, the exponent alpha is very close to 1. In the summer, it's around 0.98. In the winter, it's around 0.94. So it's very close to 1. And basically, we find what we thought would happen is that at alpha equals 1, the bats combine intensive searches with extensive searches, and they basically optimize the balance between energy expenditure and risk management. But is this only exclusive for bats? Is this behavior of revisitation with an exponent alpha close to 1 only exclusive to bats, or does it occur for other species as well? We wanted to check this, and this is ongoing work now. We wanted to check this for other species, which I will show you also in the next slides in another aspect. So we looked at kites, kestrels, vultures, owls, ravens as well. We have many, many data sets for many species. And we wanted to see whether this model is adequate for these species as well. For example, we looked at the mean number of sites as a function of time for the black-winged kite, and we could fit it indeed to a straight line and find the exponent beta, which is which comes out to be around 0.6, not very far from the fruit bats. You can also look at the probability distribution of the number of visits as a function of the number of visits. This is the exponent, the graph that I showed you in the beginning. And you see that this is a straight line as well. You can connect the exponent here, gamma, to mu or beta, doesn't matter, only if alpha equals 1 in the theory. So for alpha equals 1, there is a very simple connection between these two exponents. For alpha different than 1, it's very complicated to connect, but you can do it numerically. So what we conjecture is that for species where gamma equals 1 plus mu, so these are two different graphs, of course. So when gamma equals exactly 1 plus mu, we know that alpha equals 1 in the model. So we know that they operate at the working point of alpha around 1. And by looking at the various species, plotting the value of gamma as a function of mu, we see that the fruit bats, black-winged kites, and vultures are very close to alpha equals 1 indeed. And other species like the common kestrels and the barn owls, adults and fledglings, are not very far from that. So there are other interesting things that can be computed. For example, the site entropy, where you calculate this quantity here, and the entropy is minimized when the individual or when the species visits only one tree, when the individual visits only one tree, and maximized when all trees are equally visited. So, of course, this entropy is related to alpha, and you can combine these exponents and get some very interesting results. Okay, so I will continue now to the next part of the talk. Now I want to tell you a little bit about ergodicity breaking in area-restricted search of avian predators. Yes, question?
Maybe this question, is it understood how the bats implement this alpha equal 1 strategy? Like, what is the way in which they, like, how does a bat make this decision such that effectively
I don't know the answer
it gets
to that.
the alpha which is equal to 1? What is the,
I don't know the
mechanism?
mechanism. It's a good question.
That needs to apply to get this alpha equal 1.
It's a good question. I don't think this is known, but the fact is that they operate close to that. It's reasonable for a physicist to think that, but of course the underlying mechanisms are complicated, of course. There is also correlation between bats flying from the same cave, so I haven't talked about that at all. I've assumed that each one is an individual that doesn't have any correlations. So of course there are correlations, they fly together, but the fact of the matter is that it's very close to 1. Yes?
I have a related question. When I look at this, are you sure that this is actually in the bat and not given by the external circumstances? Because your alpha changes in winter and summer, isn't it? So you clearly have an external control parameter that changes your alpha. So why should it be in the bats at all?
Why shouldn't?
Why should it be in the bats due to the animals at all? The animals just follow the external energy.
Yes, but it still depends on their memory. I mean, the fact that they return to trees after 1 month means that they have quite good memory, and this was investigated in other works, independent works. So the other animals may have a much weaker preferential reattachment exponent because their memory is much weaker. So I agree with you that there are other ingredients that I have not taken into account. But assuming this very simple model, then we see that alpha equals 1 is the optimal operation point. Yeah. Yes?
I also have a question. Why probability to revisit a tree is proportional to number of visits? For example, if I go fishing and I have different lakes, and I go to this lake 10 times and catch 0 fish, I will never return. Because I have memory, but birds return, and
yes, but of course this is also a simplified This is also a simplified assumption. Probably if it happens once and it does not return anymore, then it's they will not return. But if it happens, if they return twice already, then they have a reason to return. So of course this is simplified, but it's effective. It's effective. So the more they return, the better the tree is. That's for sure. They don't return, I mean, they do have a reason to return to a tree. Okay? But it is effective, definitely. Yes, more questions?
Sorry to keep the questions going.
Sure, no problem.
The next part, but I remember it said that when alpha was 1, they went to each tree roughly equally, and the same
When alpha is small,
when it's small.
yes,
So
when it's very small.
so 1, it's still a proportion. But
One,
it's
they have a few trees. The amplitude is not the same. So there are a few trees that are highly visited, but not one tree.
Right.
Okay, that's the main difference. Okay. Yes.
Yes, just that very similar to what has been said already. If you're not taking into account in any moment the qualities of the trees or the difficulty to go to a tree that is farther away than others.
There is no difficulty. I'm just saying I haven't mentioned this, but we checked the step size distribution. We checked the distance of the trees. It doesn't matter at all if it's 30 kilometers or 3 kilometers. It doesn't matter. The fact they go in a straight line to those trees. So the distance doesn't matter here. It doesn't play a role.
The quality is like the quantity of fruits.
Of course, it is manifested by the exponent beta, the quality of the fruit.
Since the probability that you're doing is only depending on the quantity of time the guys visited the trees, actually what this alpha is meaning, maybe not necessarily the remembering of the quality of the trees or the smoothness, would be more like a parameter that governs how much we like to move. Just that.
How much would
The bat likes to move.
they like to? I didn't hear.
Move.
To move.
Explore.
I see.
Because there's no discrimination between trees at some values of alpha. And when you saw a discrimination for one tree, it's just because the guys visited just one tree and didn't like to move. That's how
But they still move a lot. I mean,
they may
this
move.
tree may be extremely far.
Yeah, they may move, but they don't like. And they tend to not move.
I mean,
Have I interpreted that correctly?
no, I think, well, alpha in this model, at least, it's the interpretation in my understanding is clear. It's how strong they return, because if alpha equals 0, then there is like a democracy. They return to each tree with an equal probability. And you assume that you have a set of trees. They don't just fly around. Okay, you have a given set of trees. So the option is to visit one of these trees. Okay? Yes.
It's a very simple model,
Yes.
but it involves an aging process where you have a graph and you start with some propensity to move to your neighbors. But as time goes on, you always choose the probabilities that equal the frequencies you've used before. So if you visited this site 3 times, and this site 5 times, and this
Yes.
site 7 times, then next time you'll go in proportion. Except
No,
there's
but
a
I
basic
divide by the overall number of visits, which grows in
Yeah,
time.
exactly. So that's what proportions are.
Yeah. Of
Yeah,
course.
so that's called a reinforced random walk. And in the line, you have an interesting phenomenon that you end up on 5 sites. You actually find eventually that an individual will concentrate their behavior on a very well-defined set of. Is that what happens here? So after time, an individual isn't very they explore
Yes, of course.
only their known world.
Absolutely. Yes, this
And
is
then,
exactly the model.
Okay,
Yes.
but there is a
Absolutely.
well-defined, quite large
Yeah.
literature because there's some hard math problems with that.
Yeah. Thank you. Okay. Can I continue? Good. Next part of the talk is ergodicity breaking in area restricted search of avian predators. And for that, I want to very briefly introduce the notion of continuous time random walk, which you heard a little bit in various talks until now. But I will put it in an exact, put the exact definition just to put everyone on the same page. So for a simple random walk, we know that the probability per unit time to go to the right and to the left is just 1/2, and we assume basically that the waiting time distribution, the distribution of times between steps is exponential here. So if we wait a very long time, the probability to remain here is 0, right? Goes to 0, and the probability to go right or left is just 1/2. So you can write down the master equation in discrete time and discrete space, and you can assume continuous time, and then you can solve this equation. You can also go to continuous space. This is very well known, all of these. D is a diffusion constant here, and it equals delta x squared divided by delta t with some constant. And you can solve this diffusion equation. It's a Fokker-Planck equation with no drift, and you get this Gaussian distribution. So the position, the distribution, the probability distribution to be at position x and time t is just a Gaussian with a maximum at 0, and its width grows in time as square root of t. So, sorry, if you plot the mean square displacement, if you calculate the mean square displacement, it's just linear in time. So this is regular diffusion, and this is a typical trajectory. But you can generalize this notion and have continuous time random walks where the waiting time distribution between steps is not drawn from an exponential distribution, but rather from a different distribution. So what is interesting to us in this aspect is distributions with a very wide tail. So distributions that have a diverging mean. So for example, a power law distribution for the waiting times, which has a diverging mean for alpha smaller than 1. And in this case, the mean square displacement grows sublinearly in time. So it grows as t to the power of alpha with alpha smaller than 1. So what describes this process basically is these long stretches where nothing happens, because you sample longer and longer waiting times, and until then, nothing happens basically. So you see these long stretches, and the motion is much slower. Of course, instead of having, or in addition to having a generic waiting time distribution, you can also have a generic step size distribution, and you can get Levy walks here if you take a distribution of step sizes with a diverging variance, for example. But we will focus on waiting time distributions with a diverging mean. And remarkably, you observe these waiting times when you look at searches of these various species, owls, kites, and kestrels. And I will show you that this leads to the fact that the underlying dynamical model for these is a continuous time random walk. We will see various pieces of evidence for that. Okay, so the system that we we have tracked. We have used an innovative tracking system called the Atlas, which is basically a reverse GPS device. Instead of performing the calculations on the chip itself, the radio signal is sent to some antennas which are in the area, and all the calculations are done on the antenna. So this allows this device to maintain its functionality for a very long time, for up to 8 months, even a year, with a broadcasting frequency of 1 hertz, which is amazing in this field, because if you take a regular GPS device, you get a transmission every 5 minutes or something like that. It depends whether it is charged or not charged, but the frequency is not even close to this. So by having such a high frequency, such a high temporal frequency of data, we can investigate regimes that were unavailable until now. So for example, search. The entire search process takes up to 40 minutes for these species. And if you have a resolution of 5 minutes, then of course you cannot really you cannot really identify the underlying model. So this allows us to look at the data at the right scales. Okay, so basically the main question we were interested in is, what is the difference between the two behavioral modes here that are present here? You see, this is a typical trajectory of a black-winged kite, similar trajectories for barn owls and common kestrels. The home range is around 10-20 kilometers. The search ground radii are around 200 meters. Of course, we checked that the results are convergent when taking other radii. So this is how a typical trajectory, daily trajectory, looks like. We wanted to understand what are the differences between the commuting and the searches What are the characteristics of these movement patterns? So if you look at the entire, you can take the data set, the time series, and just calculate the time average square displacement. And you get some exponent here which is slightly above 1 here. But this is meaningless because without segmenting, you don't really know what you're looking at. So first of all, we took the the time series and segmented or divided it to segments, searches and commutes. We did that by detecting switching points. We can do it by using various metrics. Here we chose just the switching points, the mean, basically the time it takes to exit the vicinity of each point. If it was short, we concluded that it's part of a commuting. If it was long, concluded that it was part of a search. So we performed the segmentation, and then we calculated the time average square displacement for the commutes separately and for the searches. And we see a completely different behavior. While the commutes are super diffusive with an exponent close to 2, almost ballistic, the searches are subdiffusive, and interestingly, the span here is huge. So the trajectory span a huge range of numbers here, so for each delta here. So this has implications, of course, and I will discuss this in the next slides. Okay, so let's go back to this picture, and this is the definition of the time average square displacement. And when the trajectories are highly irreproducible and all over the place, it's convenient also to look at the ensemble average time average square displacement, which is more regular. So this is how the time average square displacement looks in the commuting segment and in the search segment. But if you look at the separate trajectories which make up this ensemble average trajectory, you get a huge, very wide distribution here and a very narrow distribution here. So this is what you get for a particular choice of delta. I think here we chose a delta of half a minute. What does it mean? So a narrow distribution means that basically the trajectories are reproducible. There is a typical trajectory, and it means that the behavior is ergodic. And this, of course, we all know, this is already known. It was extensively investigated in the past that these commuting segments basically are due to long-range correlations or biases. Of course, this is understandable. But what about the searches? So the distribution of TASDs is huge here. You see the width is huge, and it actually corresponds to a Mittag-Leffler distribution. And this basically agrees with theoretical predictions of continuous time random walk. So you can fit the data to a Mittag-Leffler distribution, and the fact that it's wide and not a delta function-like distribution indicates that these are non-ergodic. The searches are non-ergodic, and the fact that it agrees with this theory of continuous time random walks indicates that we should be looking for long waiting times. I haven't shown you that yet. First of all, I want to discuss a little bit the difference between a continuous time random walk with finite mean waiting time distribution and infinite mean waiting time distribution. So here I'm showing you simulations of a bounded domain where we take the waiting time distribution to be exponential. So you see that all the trajectories more or less coincide. The average, the ensemble average trajectory is representative of the individual trajectories, and importantly, the time average square displacement is independent on the total measurement time. So there is no aging here. What happens when the mean of the waiting time distribution is infinite? For example, when taking this distribution with alpha smaller than 1. So what you see is that trajectories are all over the place. Sorry, did you? How much time do I have?
I'd say some 8 minutes.
Okay. So the trajectories are all over the place. The reason is that when sampling more and more trajectories, you see that longer and longer times are sampled. So basically, there is no typical trajectory in this case. And this is, of course, a signature for non-ergodicity, for non-ergodic behavior. Also, the fact that the total measurement, the TSD depends on the total measurement time, is indicative of non-ergodicity. It's because when you measure for longer and longer times, basically you allow for sampling of longer and longer waiting times. So from this time average square displacement, you can extract the Hurst exponent alpha, which is alpha in this case, the exponent of the MSD. And this is what we will do with the data. These are numerical simulations. And this is the data. This is real data, analysis of the empirical data for the barn owls, but similar picture is obtained for the black-winged kites and for the common kestrels. For each individual, this is, I think, 200 trajectories here, and you see that the trajectories are all over the place. There is no typical trajectory, and these calculations are repeated for all individuals. So in addition, you see the dependence of the TST on the total measurement time. So we clearly conclude that the motion is non-ergodic and subdiffusive here, and we can extract the value of alpha for each individual and for each species, and these are the values that we find. So all of them are subdiffusive. For the owls, it's around 0.65. For the kites, around 0.51, 56. Depends whether adults or fledglings. And for the kestrels, we find that it is 0.51. But still, we are missing the smoking gun of the waiting time distribution. Now, we wanted to check independently the waiting time distribution by looking at this search area here or here, and dividing the search area into small radii of around 15-20 meters. This is larger than the error, the typical error of the GPS, which is around 5 meters, but much smaller than the radius of this entire field, which is about 200 meters. So we calculated the time it spends in each of these until it jumps to the next circle, basically. And this is the distribution that we have found. This is a power law with a cutoff. Power law with a cutoff at around 40 minutes. So we found this functional dependence with some multiplied by an exponential, which has a cutoff at around 40 minutes. We will talk about this 40 minutes soon, but remarkably, the value of alpha from this graph, which we extract, is almost identical to the values extracted by looking at the TASD. So these are two independent evidence, parts of evidence, pieces of evidence that show that the underlying model is a continuous time random walk. So the bird doesn't know anything about continuous time random walk, of course, but the waiting time distribution and the behavior of the TSD both are consistent with CTRW. Finally, I want to look at so-called stop duration, distribution of stop duration. How long the birds spend in the search area, in the entire search area. So this is the probability distribution to be for a duration of t in the search areas. Okay, this is averaged over the entire population of owls, kites, and kestrels. And we see a clear behavioral shift at around 40 minutes for all species. So, and this means, and this of course we check that it doesn't depend on the radius as long as the radius is sufficiently large. And this means that there is some sort of a functional gain, that the functional gain for a longer stop is diminished at some point and the bird just is driven or just flies somewhere else. Okay? I want to summarize this part. I have shown you that commutes and searches display a markedly different stochastic properties. Commutes are ergodic and super diffusive, whereas searches are non-ergodic and subdiffusive. The fact that commutes are ergodic means that there exists a typical flight trajectory, but there isn't a typical search trajectory. So the search trajectories are irreproducible and unpredictable, and the take-home message basically is that while there are only few ways to commute, there are many ways to hunt. Hunting is irreproducible, unpredictable, which may be evolutionary beneficial. The fact that for the foraging tactics, of course. And finally, I want to say, I'm not going to talk about this because I'm out of time, but we have some recent works on the implications of this population dynamics, basically with long waiting times. So imagine that you have a predator-prey model or some other model of rock, paper, scissors, where the interactions occur with a waiting time distribution which has a diverging mean or very wide tail. So as we see here, as we have seen here, this has dramatic implications, and we have shown in these works that there are implications on quantities like the mean size of the population, the stability of the fixed points, and even rare events, of course, even rare events such as mean time to extinction or switching times. So we are currently investigating these models in these works. And finally, so I'm skipping this. I want to thank my collaborators, Ohad Wilk, who was my PhD student. He has now graduated, Ran Nathan and his group, Vicente Mendez and Daniel Campos from the University of Barcelona worked with us on the BATS project, Ralph Metzler, who worked with us on the Anomalous Diffusion project, and Mauro Mobilia, with whom we worked on the rock, paper, scissors projects under non-Markovian, with non-Markovian processes. Thank you for your attention.
We have time for some questions. Yes, please.
Thank you for the talk. I think I missed it. Did you calculate the time average mean square displacement for waiting time for stays in waiting time periods?
The time average square displacement?
Time average mean square displacement for...
Yes, for the searches.
For searches, yeah. Was
Yes.
it power or...
Yes, this is it.
yeah, so what was
Here.
the exponent here?
Exponent here is, these are the values. So we can extract the value of alpha based on this theory, and these are the alpha values. They are consistent with the waiting time distribution.
How can it be that it's known that for CTLW the time average mean square displacement goes linearly with
No, this is bounded. This is bounded.
Okay.
You're right. In the unbounded case, it goes as delta. But in the bounded case, it's delta to the power of 1 minus alpha.
Okay, so
Yes, absolutely.
yeah, thank you.
You're welcome. Yes.
So on the last slide that you showed, you talked about there's one way to commute, but lots of ways to hunt.
Yes.
I mean, clearly there's kind of unpredictability in that search part of the process. But can you tell whether that unpredictability is to do with different strategies, different behaviour, or is it just unpredictability in the results?
I mean, I can't answer that again. These questions are beyond this research. How the animal, what is going on in their head, but the fact that there are long waiting times makes their trajectories unpredictable. It's because you sample from a distribution with a very, very, very long tails, and then you can get basically any result. The more you sample, the wider the range of the results is. That's what I can say. Yeah.
Reinhard?
Yes.
Is there individuality in the flights of your birds? Individuality, meaning that different birds fly differently because of size, age,
yes.
Whatever.
Yes, definitely. There is a distribution of speeds of I haven't shown you this, but maybe I have one. I don't know if I.
It's meta, right? I mean, how does it show up?
Here you can see that the distribution of waiting times for all the species here, for example. So there is a variability, definitely. The cutoff is a little bit different. The speeds are a little bit different, definitely.
Okay, but you argue that the time dependence is still the same for all of them.
Yes,
only the parameters matter.
yes, exactly.
So then you could rescale in principle. That's what we did for the bumblebees. So they all flew with in the same style, but with different parameters. So we could rescale, but for the turtles, for example, no way. I mean, they all swim totally differently.
Interesting.
So therefore, one has to be careful.
Yes, during commutes, the variability is small. During searches, it's larger, but still you can do the rescaling. Yes, absolutely. Yes.
There's a following question.
So actually you take minimum this 40 mils, so the tails are not heavy. You have bounded random variables. Did you try to fit, say, wave wool distribution? So they are not heavy tail, but maybe try some hypothesis testing.
Yes, absolutely. We have that in the paper. So best fit, so it was worse than the power law. Definitely we tried. Yes. You're right. I mean, we have 2 orders of magnitude here, not more. Yes. But that's already significant for this type of data. I mean, sometimes it's only 1 order of magnitude. But I agree with you. I mean, that's not a proof that it's a power law. Of course not. But it was better than other attempts.
And are there some explanations of these power laws?
They perch, they sit and wait. Of course I can't know what they are thinking.
I mean, informal explanation.
Yes, but they wait, they sit and wait in some shaded areas, but sometimes they just sit and wait to see the prey coming out from the hole in the ground, some mouse or something, and then they attack. They don't move around. For some reason, they know that moving around is not good for them. It's less beneficial than waiting at some point and just looking, because they have an extremely good sight, vision. So they see the entire field. I mean, most of the field, not the entire field. Yeah.
More questions? Well, if there are no more questions, we thank Michael again.
Thank you.